This sound killed careers. This engine rewrote racing history, and this secret almost destroyed Chevrolet. The 265 wasn't just revolutionary, it was a ticking time bomb, praised as a superpower pack by day, cursed as the oil-starved assassin by mechanics at night. Why did drivers risk their lives for it? How did it crush Ford on the track while tearing itself apart from within? The truth is darker, deadlier, and more dramatic than you've ever been told. Birth of a revolution. Ford's 1954 Y-Block V8 wasn't just competition, it was humiliation. Studebaker? They had a V8 Chevrolet, GM's sales king, stuck with 6 cylinders while 50% of buyers demanded V8. GM manager Thomas Keating's 1952 memo was a scream for survival. Flint, Michigan became ground zero. But who could design an engine to save Chevrolet? In 1950, about 26% of new car buyers wanted a V8. By 1952, that number had climbed to 33%. By 1954, half the market was demanding V8 engines. Chevrolet's general manager, Thomas Keating, didn't mince words in a 1952 memo to GM's top brass. "We've become too six-cylinder-minded." His warning rang alarms at GM headquarters, sparking a decision that would become known as GM's billion-dollar gamble. New factories were purchased, including massive facilities in Flint, Michigan, to birth a V8 that could reclaim Chevy's crown. Edward Kelly, the revered engineer behind Chevy's legendary Stovebolt 6, was tasked with designing the new engine. Kelly was well respected, no doubt about that. But by the early 50s, many around him believed his ideas were starting to feel a little outdated. The first serious attempt at a Chevrolet V8 under his watch was essentially a downsized version of Cadillac's 331, which had been launched in 1949. Kelly's version displaced 231 cubic inches and was nearly ready for production when a major shift happened. In May 1952, a rising engineering star named Edward N. Cole was brought in to take over the project. Kelly was reassigned to oversee manufacturing, while Cole took charge of breathing new life into Chevrolet's engine program. And it didn't take Cole long to spot a problem. The Cadillac-style V8 was too heavy, too costly, and had almost no room for future growth. Cole knew this wasn't just about horsepower. It was about building an engine that could be mass-produced efficiently, cheaply, and with room to evolve. He realized Chevy needed not just a new engine, but a new way to build engines. For Cole, manufacturing cost was just as important as any horsepower number or compression ratio. The Mastermind and the clean sheet. Talking about the version developed under Edward Kelly, Cole didn't mince words as he reportedly said, "You don't tweak an old design. You start with a clean sheet of paper." And that's exactly what he did. And that clean sheet approach didn't just apply to styling or performance, it extended all the way into the engine's manufacturing process. Cole's team reimagined how to cast the engine block, starting from scratch. He believed there were smarter, more efficient ways to build a better engine. More precise, more cost-effective, and still powerful. The breakthrough came with the decision to use green sand cores, specifically in the valley between the bores, that critical 90-degree angle at the heart of a V8. Traditionally, engine blocks used dry sand cores, but Cole's team realized that by replacing most of them with green sand cores, they could cast the entire block upside down, because it allowed them to precisely position the plate that held the bore cores, giving them tighter control over wall thickness. That meant they could safely cast walls as thin as 5/32 of an inch, a game-changer for weight and efficiency. This casting method wasn't Cole's idea alone. He credited John Dolza from the GM engineering staff, saying he had as much to do with that as anybody. Together, they pioneered a new block casting technique that allowed for unprecedented precision in cylinder bores and marked a major milestone in thin-wall engine casting. At first, Chevrolet's new V8 was planned with 245 cubic inches of displacement. But engine displacement was rapidly becoming a bragging right in the 1950s horsepower race, and to keep up with market trends and the competition, Chevy engineers bumped the number up to a range of 260 to 265 cubic inches. Ultimately, the latter was chosen. One of the most important early decisions was setting the bore centers at 4.4 inches. That simple measurement determined a lot, from the overall length of the crankshaft to the compact dimensions of the engine block itself, only 21.75 inches long, remarkably small for a V8. The final product was dubbed the Turbo Fire V8, and it was more than just a marketing name. It represented a forward-thinking, precision-engineered design. This new V8 was over-square, meaning its bore was larger than its stroke, which allowed for higher revving performance. It featured hollow push rods, stamped metal rocker arms, and an intake manifold that also served as the valley pan, a smart way to save weight and reduce complexity. Engineers built it with interchangeable cylinder heads, aluminum pistons, and a high compression ratio for the time. It also had fully water-jacketed ports, allowing for better cooling, and wedge-shaped combustion chambers that improved combustion efficiency. And instead of using a cast-iron crankshaft like many others, Chevy opted for a pressed-forged steel crank, stronger, more durable, and a sign that this engine was built to perform. But the 265 V8 wasn't just compact, it was brilliantly engineered. It boasted a stroke-to-bore ratio of 0.8 to 1, one of the best ever achieved at the time in an over-square design. That meant less piston travel per mile, lower internal loads, and most importantly, reduced wear on the pistons, rings, and cylinder walls. In other words, it was built for both performance and longevity. The engine also came with an 8.0 to 1 compression ratio, which was fairly high for the era. That boost helped improve both power output and fuel economy, a win-win for drivers. And thanks to the rise of higher-octane fuels, engineers were already dreaming of pushing compression ratios to 12 to 1 in future production engines. Another standout feature is its compact block length, which is less than 22 inches. That gave the engine incredible structural rigidity and left plenty of room under the hood, making maintenance and repairs a whole lot easier for everyday drivers and mechanics. One of the remarkable features of the 265 was its wedge-shaped combustion chamber. This design included a large quench area, a flat surface that helped control detonation or engine knock. But it did more than that. As the piston moved upward, it forced the air-fuel mixture away from this quench zone, creating turbulence. That turbulence helped mix the fuel and air more thoroughly, leading to faster, more complete combustion. Chevy engineers also nailed the spark plug placement right in the hottest part of the combustion pocket. That meant the flames spread quickly and evenly, delivering smooth power with minimal risk of knocking. And they didn't stop there. A clever lip on the cylinder head extended slightly over the cylinder bore, acting like a shield. It protected the spark plugs from any oil the piston rings might scrape up, helping ensure reliable ignition every time. Engineering marvel or Trojan horse? As compression ratios climbed during the 1950s, engineers had to get serious about preventing detonation. But boosting compression was essential. It gave engines more power and better fuel economy, which was a win for both performance and efficiency. What made those higher compression ratios possible is the tetraethyl lead, a fuel additive that helped keep everything running smoothly without knocking. The cylinder heads were also interchangeable. That meant no need to manufacture separate left and right versions, which simplified production and helped keep costs down. Clever engineering all around. The hollow push rods in the 265 were a clever solution, allowing oil to splash up to the rocker arms and valve stems without needing extra oil lines or complex passages in the heads. While the concept wasn't exactly new, engineers had been using hollow push rods for decades, Chevrolet's execution still required innovation, especially when it came to the rocker arm mechanism. Engineer Harry Barr reportedly recalled there were problems with the hemispherical ball, the mating surface of the rocker arms, also in the amount of the oil that came up through the hydraulic lifters. One of our engineers, Bob Pappenguth, came up with a little wafer, a method of metering that oil in the lifter, a little log jam that was essentially overcome. They also had to deal with uneven oil distribution between the rocker ball and arm. The solution? designing a slight mismatch in contact surfaces so oil could properly flow between them. But even then, the job wasn't done. When the engine first hit production, some early units suffered from squeaky rocker balls and other teething problems. To address lubrication throughout the system, 3 horizontal oil passages were drilled into the block, 1 main gallery and 2 tappet galleries. Oil flowed from the high-pressure main gallery through a hole in the rear camshaft bearing shell and onto each tappet gallery, maintaining consistent lubrication even under demanding conditions. The stamped sheet metal rocker arm, a simple yet revolutionary piece, was originally developed at Pontiac by engineer Clayton Leach in 1947 while working on their V8 engine program. Although Pontiac's engine didn't launch until 1955 due to several delays, Leach's rocker arm design would go on to influence the entire industry. When Chevrolet engineers began developing the small block, they consulted with their manufacturing team and quickly realized something big. The stamped rocker arm could be produced with 0 machining. That was a game changer. It enabled a lightweight valve train design, which in turn allowed the new small block to safely rev up to 5,500 or even 6,000 RPM, a big deal for performance at the time. But there was still one challenge: lubrication. As Clayton Leach explained in an interview with automotive historian Michael Lamb, Chevy had to drill a small hole in the pushrod socket to get oil to the rocker arm without flooding the combustion chamber. That tiny adjustment kept the engine reliable while still cutting costs. Even the rocker arm covers got special attention. Ed Cole, the chief engineer, wanted them to look as good as they performed. Within budget limits, he insisted they have style, leading to the now iconic Chevrolet script elegantly stamped across the top of each cover. Chevrolet's TurboFire Phi 8 wasn't just about power. It was a study in smart, efficient engineering. One of its standout features was its fully water-jacketed ports, paired with aluminum pistons, which gave the engine superior heat dissipation. This better cooling meant Chevrolet could use a lighter radiator, trimming both weight and production costs without sacrificing performance. The engine's autothermic slipper-type pistons, fitted with 3 rings, included a circumferential expander behind the oil ring. This ensured consistent axial and radial pressure to help control oil burning. Even better, the piston pins were press-fitted, a clever move that eliminated the need for a split rod and locking bolt, simplifying assembly. Thanks to its short stroke design, the connecting rods remained compact. Combined with lightweight aluminum pistons, this kept the engine's reciprocating mass low, which improved response and efficiency. But it didn't stop there. Chevrolet engineers also revolutionized the crankshaft design. Using advanced forging techniques, they created a shorter, stiffer crankshaft that naturally reduced torsional vibration. Internal testing confirmed it. Vibration levels were consistently smooth across most of the RPM range, with no sharp spikes. A harmonic balancer cleaned up the remaining resonance. To keep everything in sync, Chevy introduced new balancing technology. The crankshaft was first partially balanced, using a machine with electronically controlled indicators, then final balancing of the fully assembled engine was done on a separate device that could pinpoint the exact out-of-balance position. The solution? The machine simply drilled precise amounts out of the crankshaft counterweights at the front and rear until perfect balance was achieved. Another key innovation that helped tame engine vibration was Chevrolet's Poised Power engine mount system. Used on both the V8 and the 6-cylinder, this dynamically balanced 4-point setup was engineered to minimize how much engine torque transferred to the frame and body. The secret? The mounting points were angled so that the resulting roll axis absorbed most of the engine's movement, leaving only minor vibrations to reach the rest of the car. At the front of the engine, Chevy used 2 strut-type mounts. Each one featured 4 circular rubber biscuits stacked around a metal spacer stud. These studs were secured to brackets at the lower corners of the cylinder block and sat perpendicular to the seat of the front cross member of the frame. To reduce vibrations, the rubber biscuits were placed on both sides of the bracket and on both sides of the cross member. At the rear, 2 shear-type mounts were placed at the lower back edge of the clutch housing. connecting the engine to brackets that were welded to the frame's side members. These mounts were made of two metal brackets separated by bonded rubber, which allowed the rubber to flex under shear stress when the engine rolled and under both shear and compression when supporting the engine's weight. The result? A much smoother ride and better isolation from engine vibrations. The deadly secrets. Yet for all its brilliance, this engine, in its original form, could kill itself from the inside out. One of the reasons is Chevy's decision to launch the 265 without a full-flow oil filter. Flaw 1. The murderous oil system. The 1955 engine launched with only an optional bypass filter, filtering just 10% of the oil. Smokey Yunick, legendary builder, raged. Chevy gave us a great motor, but forgot to keep it alive. It was an oil-starved assassin. You prayed it didn't chew itself to death before 30,000 miles. Flaw 2. The expanding pistons of doom. Tight clearances saved weight but were deadly under heat. Pistons expanded, scouring cylinder walls. Mechanics dubbed it the scuffer. Southern heat or track use meant near-certain seizure. Flaw 3. Missing essentials. No PCV valve, primitive breathers, rudimentary cam lubrication. Automotive historian Dave Emanuel confirmed, the 265 was a prototype rushed to market. Chevy was so desperate to beat Ford, they shipped an engineer's dream and a mechanic's nightmare. The original 1955 265 Turbo Fire relied solely on an optional bypass-style filter mounted externally. Instead of filtering all the engine oil, it only filtered a portion of it. That meant every time the engine was running, metal shavings, carbon sludge, and microscopic grit were free to ride shotgun through the entire lubrication system. This wasn't just a theoretical flaw, it was a time bomb. Internal wear mounted fast, and many engines failed before their time. Chevy scrambled to fix the oversight, and by the 1956 model year, a full-flow oil filtration system was finally standard. But the damage was already done, literally and reputationally. The piston design of the 265 was equally bold and equally flawed. Built with tight thermal clearances, the pistons were engineered for efficiency, not endurance. In real-world driving, especially in the sweltering heat of southern states or when pushed hard on the track, those pistons would expand beyond safe limits. Result? Scuffed cylinder walls, cracked piston skirts, and in severe cases, total engine seizure. Chevrolet issued technical service bulletins warning dealers and mechanics to watch for overheating signs and to inspect pistons carefully. But again, the Band-Aid came after the bleeding. While later small blocks became paragons of design, the original 265 was, in many ways, a prototype shoved into production. It lacked provisions for vital upgrades like a positive crankcase ventilation, which meant early versions suffered from crankcase pressure issues and increased oil blow-by. The oiling passages were rudimentary. Breather systems were minimal. Mechanics quickly learned that retrofitting these early engines was a chore. Not because they were poorly made, but because they were designed in a rush to revolutionize. Even the camshaft lubrication system was primitive, relying on splash oiling in some areas where pressure-fed systems would later take over. Automotive journalist Pat Ganal wrote in the small block Chevy Bible, "It was a brilliant engine with a dark side. Chevy bet big, but they didn't sweat the small stuff." Why it was still legendary. Despite these deadly flaws, the 265 engine would go on to form the DNA of countless small-block Chevy engines. In just 15 weeks, Ed Cole's team of 2,900 engineers, including Assistant Chief Engineer Harry Barr, turned a concept into a running prototype. By 1955, it was in production, offered in two versions for most of the model year. Buyers could pair either engine with a standard 3-speed manual, an optional 3-speed with overdrive, or the Powerglide automatic. The base 265 featured a Rochester 2-barrel carburetor, delivered 162 horsepower at 4,400 RPM, and pushed out 257 pound-feet of torque at 2,200 RPM, all for just $99 extra over the standard inline 6. Shortly after the model year began, Chevy introduced the Power Pack version, a hotter 265 with a Carter 4-barrel carburetor, a special air cleaner, and dual exhausts, except on station wagons due to fuel tank design. It churned out 180 horsepower at 4,600 RPM and 260 pound-feet of torque at 2,800 RPM, and it added just $59.20 to the base V8 cost, making it a performance bargain at $158 total. For second series 1955 Chevy pickup trucks, there was also a detuned 154 horsepower version with 7.5 to 1 compression. And just before the end of the model year, Chevrolet dropped a surprise. The Super Turbofire version, boasting a full 195 horsepower, a serious punch for the time. Compared to the six-cylinder Chevrolets of 1953 and 54, the new 1955 V8 were a massive step forward in performance. For context, a 1954 Bel Air equipped with a Powerglide automatic took around 18.1 seconds to hit 60 miles per hour. But swap in the 180 horsepower V8 from 1955, and that time was cut nearly in half, according to Motor Trend's road tests. It was a night and day difference. The response from buyers? Overwhelming. Chevy's new engine plant in Flint, Michigan was running flat out, but it still wasn't enough. Production had to be ramped up at the Tonawanda, New York, just to keep up. Even then, demand outpaced supply, and Chevrolet actually lost some sales because customers didn't want to wait for an engine model. Still, the appetite was clear. 43% of all 1955 Chevrolet buyers chose the 265 V8, a number that proved just how right Ed Cole and his team had gotten it. The 265 compact design, innovative casting, and scalability laid the foundation for Chevy's small block dynasty. Its DNA would power engines for decades, from Corvettes to Camaros. Track glory and bitter rivalry. Despite its self-destructive tendencies, the 265 Turbofire was a track monster. With the Super Power Pack 4-barrel dual exhausts, it dominated NASCAR. Herb Thomas won 12 races in 1955, including the Southern 500, piloting the number 92 Smokey Yunick-prepared Chevrolet. Thomas reportedly said, "This little mouse has the heart of a lion when it stays together. You gotta nurse it, but boy does it run." Buck Baker won 3 races in 55, including the Charlotte Speedway event in the number 87 Chevrolet. Baker was blunter. "It made power Ford couldn't touch, but you listened for the death rattle every lap." Tim Flock grabbed 18 poles in 55 showing raw speed. Chevy snatched 38 NASCAR wins in 1955, crushing Ford. The rivalry turned white-hot. Ford engineers scrambled, while Chevy teams lived in fear of the next engine blow-up. It was glory balanced on a knife's edge. What If's climax. The 265 Turbofire is a story of brilliance, betrayal, and bare-knuckled survival. But what if? What if Ed Cole had just one more year? Would the oil-starved assassin have been stillborn, replaced by a reliable legend from day one? What if Ford's Y-block hadn't forced Chevy's panic? Would the small block revolution have ever happened? Or would Chevy have faded into six-cylinder obscurity? What if those early failures had killed Chevy's reputation? Could Ford have ruled the 60s muscle car era unchallenged? Was the 265 a necessary sacrifice, a flawed savior, or corporate malpractice disguised as innovation? The engine that won races and then self-destructed. Was it worth the gamble? You decide. This is Paul from Rare Car Stories reminding you to dig deeper. Question everything. I will. See you down the road.